mechanism that how we actually do this for reinforcement learning. So I'll just skip this. I'll just skip this thing for now. So overfitting, so that's very important. So we talked about overfitting, we looked at these examples, and we saw that in the feature selection that we were doing in ovarian cancer, if we go more than 40 features is giving me the lowest classification error, misclassification error, but it is overfitting my test data. So it is not generalizing, it is not generalizable to unseen data. So that's what we want. So the first thing is I want to have regularization. I want to penalize those models that are completely chasing my training data or my training performance. I want to maintain judicious simplification of the model. I don't want a data set, for example, we looked at, if I just go back, if you look at this example, this is a simple model, this is a complicated model. It's a it requires a polynomial, maybe a piecewise polynomial or what, it's a high dimensional function. It's a simple linear classifier here or linear surface here. So my regularization is saying that I want to penalize any complexities or extra complexities that actually destroy the simplicity of my model at a cost of little performance. And I'll talk about what that cost is. So there's a regularization function which I'll talk in a moment, that it is just penalizing any deviation that I'm having from more judicially simplistic models that I have here. Another way is that we have to validate. That's very important. You always split your training data into training and validation data. That's what we did. If you remember, we had 160 out of 216 samples. I actually had 160 was training data and 56 was validation data. So you always separate a validation component from the training data that you use to guide your learning. So that's very, very important. And another way, if even let's say that you chose out of 200 subjects, let's say you chose 150 as your training data, 50 as your validation data. But who says you can't have overfitting there? So what cross-validation does, it does that process 10 times. It randomly generates 10 different copies, one with 150 examples, one with 50 examples. Then it reshuffles it again and samples another set of training and testing data. It does that 10 times, so even your selection of validation data set is random. So that's what we are trying to do. So validation we just studied, because that's what we did in the ovarian cancer here. So now we have a new nomenclature that is out there. So initially we had a training data and a testing data, that's all. Now we are saying we are not going to touch this novel data, but we are going to split my training data into two components. Both are completely annotated. One is a training data, one is a validation data. And that case where we are looking at ovarian cancer, if I can just run it again. So again, in this case, I call it test size, but that's validation. That's what we did. So in this case, that's what we did. We used this validation data that we extracted from the training set, and we found that with 40 features, we are getting overfitting. All the 40 features was giving me the lowest classification error, or close to the minimum classification error, but it is not generalizable. So that's cross-validation, or simply validation is one method, and regularization is another method for overfitting. And that's what we do here. If you look back, we had just this loss function. I now add another cost function here. It's a penalty parameter. This is a data fidelity term. Now this parameter is weighting how much influence my regularization should have over this loss. It's a trade-off. So if mu is 0, I go back to an unregularized supervised learning problem that I looked at earlier. But now I have this regularization function. And all I'm saying is the following, that if my current theta is deviating away based on this regularizer, penalize it. And it could be anything. Let's look at one of the cost functions, that's the Euclidean norm. Euclidean norm, this is nothing but the kinetic energy of my parameter vector. I'm looking for low energy solutions, smooth solutions, that's what I'm looking at. So if my theta has a maximum energy, this mu will rise and it is going to penalize. And it's going to say, no, you are not an admissible candidate because you have a lot of energy and you're increasing more disturbance in my parameters, and I'm looking for more smoother solutions. So I can use this regularization to avoid my overfitting. That's one. And again, what regularization you are using, that also depends on task. If you're trying to do image reconstruction where you have to preserve actual edges, which are very, very important, you have probably be using in CT imaging total variation, which is basically a one norm on the gradient of my parameters. So that's basically the total variation. In that case, theta is basically the image that you're trying to estimate. If you are looking for model selection or parsimonious representation, you are going to look at the L1 norm. And that's basically the holy grail of compressed sensing, basis pursued, lasso, penalized L1 inference, you name it, basis pursued, model selection. So you have different regularizers that you're using. And what we have a penalized objective here now. You have a data fidelity term, you have a regularizer. And mu is nothing but a trade-off that we're trying to do. If mu becomes infinity, what will be the solution to this problem? Rough, even if you don't know optimization, it would be fine. If mu becomes infinity, what will be the solution? Let's say we are using this as a regularizer. We know if mu becomes 0, we go back to the previous solution that we did in supervised learning. What if mu becomes infinitely high? If mu is very high, this term is going to outrightly dominate this data fidelity term. And I want to minimize this r theta. Minimizing this means theta should be 0. If theta is 0, the minimizer will be an all 0 vector. So even a high penalty is not good for us. So if mu is equal to 0, I go back to an unregularized problem which can have overfitting. If my mu is tremendously high, my data fidelity term is not participating anymore. It's just the regularizer, and I'm saying minimize this L2 norms. It's a very simple thing. So I'm saying minimize theta, and I'm saying norm theta squared, which is nothing but theta transpose theta. And it's an energy. And if theta is equal to 0, what's the minimum value? It has to be positive. It's a norm. It is always greater than or equal to 0. And I'm trying to minimize something that is greater than or equal to 0. The minimum value has to be 0. And this is only 0 when theta is exactly 0. So that is an uninformative solution. That's garbage. That's a trivial solution. That's not interesting. So I cannot have a mu which is very high. I cannot have a mu which is very, very small, that it is not even participating in the game. So we are always, looking for a trade-off. That's a third trade-off. There was one trade-off in reinforcement learning, exploration versus exploitation. There was one trade-off in supervised learning, that we don't want to chase our training performance at the cost of generalizability. Here is another trade-off. I want to be very careful with this regularization parameter. I don't want it to be so high that it leads to uninformative solutions. I don't want it to be too low that I'm just getting overfitted data, that it's not participating. So that's basically what regularization does. And validation we have already studied, that cross-validation is one of the most interesting ways that how do you deal with overfitting here. So I think the last slide that we have here, and I'll just revise some summary points. So we studied classification and regression. Classification simply assign classes, groups, labels. Regression assign values. Never confuse classification with clustering. I used to do that, by the way. So I was preparing these slides and I realized I have to be careful. So I always thought about segmentation, clustering, classification, labeling. I always thought that these are kind of similar. But while I was preparing these slides and I was reading different manuscripts, I realized, no, there is a subtle difference. Clustering is an unsupervised, strictly unsupervised learning problem. And when I'm talking about classification, in the context that we have studied, it's a supervised learning problem. For successful learning, I need to have unbiased training data so that it's generalizable. I need to have a regularization or validation, either of those. We usually do validation or sometimes we do both. We have to avoid overfitting, that's very important. We should always split my training and validation data, and usually it's given in one reference I read, it's 8:2 ratio. So 80% of that data should be training, 20% should be validation. And there should be a separate testing data. Usually by default, many algorithms, they do 10-fold cross-validation, so you have 10 samples. 10 times you repeat that random sampling where you have, let's say, 80% of training data, 20% of validation, do cross-validation, again, so that you want to avoid this overfitting that we have here. My data has to be rich enough. It's not, quantity is not always what is likable. Its richness, its diversity is very important. That's what we want. In most of the cases, we need to do some data pre-processing. Like in principal component analysis, you have to actually just normalize all the rows and columns so that mean is 0, because you want to find a subspace, and subspace contains the origin. So in many times when you're doing PCA, you may have to do some pre-processing. In medical imaging, we are always doing some intensity normalization, varying the dynamic range of my images, reducing some extra noise or disturbances that an image has, so that I can have an input data that is as pure as possible. without compromising on the details, which is important. Classifier, very, very important. We have to appropriately choose the classifier. We need to know what our classifier is doing. That's why we can't just use like Keras or Python or हम उसकी एक programming ले आएं और हम कहें अच्छा भाई classifier. We need to know what that classifier is doing. And that comes back to the very first two slides I showed, that it does not supplement the course where you actually study the properties of what each classifier is doing, why should we prefer an SVM classifier over a logistic classifier, and things like that. And it should also be an appropriately chosen loss function. So these are very, very important. That it is a classification problem or it's a regression problem. And we looked at that in one case, we transformed a classification problem into a regression problem, which is possible. So that's about it. If you have any questions, do let me know. Ji.